Yeah. Okay. Yeah. Up to 1/3. Yes. Okay, welcome back everyone to the post-tea break session. As you heard from Stephen, MWA marks a very significant milestone with the completion of our phase 3 upgrade. So Andy and Greg and team are going to tell us all that has gone behind the scene to make that magic. So Andy is going to tell us the part 1 of the story, and Andy is the MRO site coordinator. Over to you. Yes, you can use that mic.
Thanks, Ramesh. Hello, everyone. As Ramesh said, I'm Andy McPhail. I'm the MWA Operations Site Coordinator, and we're going to discuss exactly what's on that slide there. It's a rather long title. And I hope to tell a story about what field equipment has been developed or procured to change the MWA telescope, moving from phase 2 telescope to a phase 3. So correlating 128T to a 256T telescope, and what effect that new equipment and those design efforts have had on the infrastructure of the telescope. But I'll just introduce the ops team a bit at first. As I mentioned, I'm a member of an ops team. I'm not just the one person that did all of this. And to a large extent, I'm just the bus driver of the bus, and the engine of the ops team are the people I'm about to introduce at the moment. If we think about the MWA ops team, it sits somewhere between 10 and 12 people, generally fluctuates in numbers relative to intakes at Greylands Mental Institution, but that's how it goes. And the ops team is split into 2 groups. We have the field team, otherwise known as the cool group, and then we have Greg and the software team, which is the not so cool group. And I'm just going to introduce those team members now of the field team, who largely looked at the field side of the telescope. A few of them have made the mistake of being here today, so I'm going to embarrass them and make them stand up and introduce and point them out. But before I roll into that, I'll just make an announcement. I'm going to be discussing some fairly complex engineering stuff in very general terms. There's 2 reasons for that. I've only got 30 minutes. And the second reason is, some of you at some point in time, if I keep rambling on, will decide 20 years for murder is probably acceptable just to make me shut up. So let's roll into the field team. We've got Luke Verdun. He's our computer-aided designer and mech-eng specialist. He's the classic example, or the living example, of why you should never let a mech-eng person near any electronics. He's currently banned from site because he broke the coffee machine. Philip Gersh, our highly qualified, extremely knowledgeable, skillful electronics technician, and our human app for finding stuff on the web to buy. A lot of our stuff could not be done without the input of Phil. Jake Jones, our FPGA whisperer. Jake, where are you? Stand up. The only member of the cool group with a cool name. And then Dave Emmerich, where are you? You were here before. Stand up. He's hiding up the back there like he always does. He's our Encyclopedia Britannica, Wikipedia master of everything MWA. He's been with the MWA since 2013. Your first hire? 2009. Yeah. Your first hire. Do you regret it or not? And then Venus, another of our electronics technicians, highly skillful, highly qualified, very knowledgeable, mother of 3 young boys under the age of 5, with her sister owns and runs a retail business, just about to finish her law degree, if she was a battery, her amp hour rating would be unlimited. So and then Andrew Williams, he sits between the two groups. Andrew, stand up. He's going to give a talk soon anyway. He's our token non-cool member of the cool group. He is the president of the Python is the only language to ever consider. Some call it a cult, but we'll just leave it there. And then Carrie, stand up. Carrie Wintle is third from the right there in that photo, exercising his out-of-school hours hobby of dressing in bright orange clothing and jumping up and down on bridges in Perth. I've been waiting a long time to use that photo. Carrie is also a very experienced and qualified electronics tech. And without these 7 people, the field side of what I'm about to discuss for the telescope truly would not have come off. So when phase 3, as Stephen mentioned, it sort of evolved. We started to really look at, quite a few years ago now, what phase 3 would look like. It was all very well and good to say we want to do 256T telescope, but what else was required? What was required to achieve that? And we started to look at the finish point, which is essentially that sentence there, looking at what was required on the field side to get to 256T and by when, which was end of financial year 2024-25. And our start point, and then we defined our finish point, and we started with our start point. And we had our start point was, we had 16 shower receivers, and they came from Shao. And if there are any of our colleagues from Shao here today or online, thank you for that bit of kit. It is a great bit of kit. And as Stephen pointed out, with the photo of the box earlier, if you lift the lid on the box, it's basically got 4 components. It's got a bit of receiver magic in it. It's got an analog signal conditioner. It's got a power supply, and it's got a clock splitter. But that's all that's in the box. It doesn't have everything else that's required for a receiver system complete. We also had 16 RRI legacy receivers that were already operating 128T. So what we're essentially being asked to do within the ops team is to create another 128T telescope and then bolt it on to the 16 RRI 128T telescope. We had our lessons learned from 10 plus years of maintaining, sustaining and operating the RRI. Dave Emmerich was our fount of all those lessons that we learnt. And then the skills, knowledge and ability within the team. We needed to stay within the team. There was no luxury of time available to go outside to get training or outside support. We needed to get cracking on this because it was a big project and we needed to get it started. And then we kind of said to ourselves, well, what don't we want to do? What do we want to set? Where do we want to set our red lines and never cross them? And these were, the answer to that question, what we don't want to do was largely, let's not invent the wheel or reinvent the wheel. If it's available in the commercial world, let's buy it. But before we buy it, let's make sure it's supported in Australia and someone else is using it that we can learn from them and learn from their mistakes. That being supported in Australia came about from our work with SKA. You're all in the educational research space. You all wear more than one hat, same with the operations team. And part of the work being done to build phase 3 MWA.
Sorry.
Okay. Whilst we're working on phase 3 MWA, we're also working on SKA support, and we're also doing other work within CAIRA and things like that. And from our wider tasks that we're involved, we learnt very early on that when you receive a bit of equipment that isn't supported in Australia, you're just creating a lot more work for yourself when it finally breaks, and you need to get it either replaced or repaired. So we really didn't want to cross that boundary. And we needed, as I said, we needed to leverage the skills within the group. We wanted to incorporate improvements to the new equipment to improve reliability and resilience. I'm sure if you're a devoted watcher of the telescope, you've noticed that every time we have lightning on site, it goes down pretty quickly. So what did we wanted to do? One of the things we wanted to do in this opportunity we had with the phase 3 was to get it harder, get the telescope harder, more resilient to some of those weather effects. And personally speaking, I wanted to improve the technician comfort and ease. The RRI, for any of our RRI colleagues here, it's a great bit of kit. As Stephen's mentioned, it's amazing that it's lasted this long, but bending over and working on it every day is tough. So we wanted to take the lessons learnt that the lessons about working on the RRI and make it a bit more comfortable for the techs. It's not working. Okay, so this is our start point. On the left, we have a photo of the RRI in their weather enclosure. And on the right, it's the looking down through the top of a receiver there onto an RRI receiver. And phase 3 essentially centred on improvements to the receiver fleet and everything that comes out on that. So we did the deeper dive into what makes a receiver system a receiver system. And we looked at the RRI and we went, well, it needs weather protection, it needs a power supply, it needs we looked at the RRI and we went, well, it's got weather protection, it's got a power supply, both for its internal receiver components. It powers the tiles, it powers the beamformers, powers the dipoles. It's got an AGFO, it's got an ADFB, it's got a clock module, it's got some brains in there to make it all work together, and then it's got networking infrastructure. And then we looked into, so that's basically where we had to start. And then we looked at it and compared it to the RRI. And as I mentioned, we were missing all of those components and they essentially needed to be built from the ground up. Then we looked at the wider receiver system and we went, right, it's also going to need cooling. And we needed to know what cooling systems exists. Can they support the shower receiver in the climate of the Murchison? One thing we learned, or I learnt fairly early on, was that you can either have a cooling system that will work in the Murchison, or you can have a shielded cabinet that will work in the Murchison, but finding a shielded cabinet with cooling that will work in that environment was challenging. There was nothing commercial off the shelf in terms of a cabinet that was cooled and was shielded that existed in the commercial space. And that's logical to understand. We work in a fairly unique environment, doing a bit of unique business, so it's difficult. The clock was a challenge because the shower requires a 10 megahertz and 1 PPS input. The RRI has its own MWA freak of 655 plus the 1 PPS. So the existing clock architecture on site needed to be changed and significantly upgraded to be able to support the introduction of a new receiver fleet. And then there was the look at the environmental enclosure. What form will an environmental enclosure take to give that weather protection, but also to give operator ease and access, to keep the birds out, to stop them nesting of a night time, to make sure there's no water ingress, all of that stuff when you look at weather and climate. So the laundry list of work required grew longer and longer and longer. And there was a lot of design effort went into really refining what was required, using our lessons, our experience with SKA and what we'd done for SKA to get them to where they are now, and carried that across into phase 3. So this development of the receiver, and it was a really good sort of case study of how you get that cross-feeding of technologies and skills from one project into another. I haven't mentioned there the last point, which was really important. The code development was something I sort of, as a field tech, didn't really grasp the depth of. And Andrew and Carrie and Dave and Jake spent a lot of time really working and refining and developing that code. And there's a lot of effort there that you don't see in the physical stuff that goes on behind the curtain when you're looking at that code. And then the laundry list went on. We needed to look at new clocks to support the 3 telescopes that are the 3 receivers that will be operating on the telescope. And we had a result, a very, very good result. What you see here, where's Ramesh? Where's the microphone? Ah, I'm going to walk and talk. I'm a bit of a walk and talk. Hello? Yep, okay. So in this slide on the right, you can see we've got the new Shao receiver housings. They are the large enclosures there, juxtaposed against a RRI receiver cabinet. The weather enclosure itself, which is on the outside there, it is a very large beast, and it has to be. What we were seeking to achieve was airflow around the inner cabinet to create a bit of an air gap. So temperatures on site can get up to 50 degrees C, and we needed that airflow for heat to escape before it actually hits the inner cabinet. The doors themselves provide operator protection from shade by provision of shade. And as you can see there's a really good looking bloke standing there accessing the inner cabinet, demonstrating how we get a little bit of shade protection from the doors. They're all aligned north-south with the cooling systems you can see on the southern end here. We're actually looking north onto the core of the telescope itself. Luke designed this cabinet and spent a lot of time and a lot of simulation modelling of the climate on the site to get this type of cabinet designed. He spent a lot of time working on the finishes, the actual sheet metal that was used to build the weather enclosure, and the finish itself it's a commercial finish, but what it actually does is it pushes the heat to the edges of whatever sheet metal it is, and it wicks away like water. So it's actually surprisingly, I think the guys will agree with me, it's surprisingly cool under there. You can touch that metal on a hot day, and unlike if I put a tool on the ground with my bare skin and I try and pick it up, I'll burn myself. You can actually touch that and it's quite cool to the touch, or cooler than it should be. It's quite Luke's efforts there with the design of that weather enclosure have been very, very good. This is one of our part-time techs working on the telescope, on the cabinet itself. And again, what you can see here is that we've focused a little bit here on operator comfort and ease. You can get right into the inner cabinet by removing the doors, and it allows for full access. You can get equipment in and out quite easily. It's a lot easier to remove cables and things like that and work on the receiver. The benefits of this approach, focusing on ease of operator access, obviously improves the operator welfare, but it reduces the amount of time a receiver is down. If you can get in there and quickly change a component, quickly change a cable, the receiver's down for a lot shorter period of time. Would you like to connect? Okay. This is the inner cabinet inside its environmental enclosure. The cooling system is there on the right. And again, this just demonstrates how the cabinet opens up a bit like the Doctor Who TARDIS. It just opens completely out and you can get access from all 4 corners of the compass. One significant change between a RRI receiver and a SHOW receiver is that, and this leads into your question about climate change and things like that. Because we're limited, as Stephen discussed, in how we don't have control over our resources or our money. So we have to try and make changes where we can to try and achieve some climate change benefits. And that's our focus is truly on efficiency, making things as efficient as possible. The SHOW, unlike the RRI is one receiver serving 8 tiles. The SHOW cabinet and the SHOW receiver system is 2 receivers serving 16 tiles hanging off 1 cooling system. So we're getting greater efficiency in our cooling system. We spend a lot of time looking for a good cooling system. It's an industrial cooling system. It just works. It has a higher threshold point than the RRI cooling system, so it works for less periods, but provides for less time, but provides a better cooling response than. I'm not at 5 minutes already, am I? Gosh, I am. Righto. A better cooling response than the RRIs. And this is the internals of the system. We're looking at one side of it. You've got the 2 RRIs on the right-hand side and all the timing modules and the power supplies and everything else that was created from the ground up by the team to build that receiver system. Now, I talked earlier about COTS and how important it was for us to go down as much of a COTS system as we can. What we learned early on was that one opportunity to achieve COTS straight away was in our networking infrastructure. So we went straight away for a COTS network solution, commercial off-the-shelf network solution. And then some of our other components, our clock modules, our power inlet filters, our cabinet control systems, they look to be custom-made boxes there. But if you actually lifted the lid on them, they do have a lot of commercial components in there. And where the boards and the PCBs and things like that needed to be custom-made, the aim was to use mass-produced components as much as possible, things that are supported by manufacturers and developers, so that when they come out of system, there's already a replacement already there, ready to go. So that was the development of the cabinet. We then had to look at changing and improving and building a new clock system. Now, this is the phase 2 clock. We've got our, actually that's incorrect, that slide, but on the left here, we've got the left of the slide, we've got an input into the rubidium. It's not actually 10 meg, it's a 1 PPS input into the rub. And in phase 2, there was a 10 meg output from the rub into the SIGGEN, generated the MWA freak, which then went into electrical optical conversion, which is the haystack module, if anyone follows the telescope, and then went to the RRI receiver. And the rubidium also produced a 1 PPS, which went into the haystack clock and was sent out to the RRI receivers again. In phase 3, we had a little bit of a challenge. So we needed to introduce that 10 meg all the way out to the SHOW and the NI. Had to be fibre. We bought the MWA 655 freak. We also wanted to introduce some clock monitoring as well. So this is our current clock architecture that we had to build from the ground up. And we introduced the concept of a Grandmaster clock after the rubidium, which essentially monitored and reticulated the clock signal 10 meg and 1 PPS all the way out to the receiver fleets. Again, it was all COTS equipment as much as possible. We're using the White Rabbit CERN equipment, if anyone is following that. It's now Safran equipment. It's in use by SKA as far as I'm aware. Randall, do you know if that's still working? No. Yep, it's still being used. And we have a what's known as Z16 Grandmaster clock, working at the high level of the MWA, and it splits and reticulates the clock system all the way out to the receivers. It currently has a gremlin in its system at the moment, and we'll be working on it over the next few weeks to try and resolve that. What did all this mean for the changes to the telescope infrastructure? This is a bit of a busy slide, but I've listed it, a busy picture, but I've lifted it from the phase 3 paper that it's about to come out. If you look at the top four, or for C1 to C4, is it a C? Yes, you'll see the old phase 2 telescope and how the phase 2 receivers supported the 128T. And at the very bottom, we've got the 16U Shao supporting 128T. It's all coax over data over coax. So the Shao are only coax receivers, whereas the other 4 channels, for want of a better word, are a mix of RF over fibre or RF over data over coax. There's a small green box there on C3 and C4 called the TIU. This is our efforts to try and harden the telescope. The weak point of the telescope is lightning, and we've got a lot of coax cable just lying up there on the ground. So the aim there is to attempt to reduce the amount of RF data over coax by converting it to RF over fibre. And over the next 12 months, possibly, or no, it will be over the next 12 months, we'll introduce, we'll convert 24 tiles from RF data over coax to RF over fibre. And that will, along with some hardening of the TIU, which is a tile interface unit, that will, the aim there is to harden the telescope and reduce the amount of lightning, reduce the amount of tiles that are affected by lightning. Now, 24 tiles out of 128T isn't a lot, but there are already 56 tiles there that are RF over fibre. So we're basically increasing it from, 56 plus 24. There will be some that'll be left RF data over coax, but that simple increment increase of 24 reduces the amount of tiles that are at risk of lightning. It won't reduce the risk completely, but it will reduce it significantly. I know I've covered a lot of ground there, but does anyone have any questions?
Auntie, first of all, a big thank you for you and your field team for all the tireless work that has gone in. So we have a couple of minutes, and we will probably take questions from the room first. So does anyone have a question for Andy? Yes.
Thank you. A very impressive system, but I kind of, the synchronization and of the clocks, that has to be done over the all tiles. So where are they based? In the field, in each unit, or I wasn't quite sure how you would do the,
Where
reticulation. Is there a central unit that reticulates all those signals?
Yeah. So
where is it housed?
Yes. So for those of you online that may not have heard the question, it's where is the clock system based? So for those of you that are familiar with the MRO, there's a central control building, which is located 5 kilometres away from the telescope. And that's where Greg's going to talk about the correlator and things like that. The Grandmaster clock, the clock splitting, so that photo there, that equipment there is located in the control building, 5 kilometres away from the telescope. It leaves that building on 2 different methods. The phase 2 legacy method is using the RF clock signal over fibre on the haystack clock system. So it goes to the RRIs via a fibre optic input to the RRIs. The RRIs have their own ability to generate the clock signals, but they use the input as well in a bit of black magic, which if you want to really know a bit more, grab Dave Emmerich and he can really talk to you about it. So that's the MWA frequency over fibre. The 10 meg for the SHAO leaves a gain over fibre optic. It uses the white rabbit or the saffron, primary and subordinate. The old terminology is master and slave, but I don't like using that. So it's a primary and subordinate system. And essentially the subordinate clock, there's a pulse sent down the fibre, says how long that distance is, how much time it takes, and collapses that time to 0 so that virtually, correct me if I'm wrong, Andrew, the receiver is in that cabinet with that clock, effectively. Would you agree, Andrew? Yeah. But that system, as great as it sounds, has some challenges. That's an understatement, yeah. So we're currently working through that at the moment. And if you think about this, I made this slide last night. Sorry. I made this slide last night and there's this clock monitoring box. And Jake, who's our FPGA and clock whisperer, has, we've decided as a group that that clock monitoring box sits after the GM clock and before the clock split. We've got some clock issues at the moment. So the question I'm going to discuss with the team is, all right, do we need to move that so that we can monitor what we're doing and look at their faces right now? Or do we need to create a second one and put it somewhere else in that chain? I don't know. I don't know the answer to that, but we'll work on the current clock problems that we've got and then figure out the answer to that question. Does that answer your question?
Okay, so time for maybe a very quick question, if someone has a burning question. Yes.
Thank you. I just want to ask a quick question. For the case you said to host the receiver from Shaw, do they need any modification to suppress the IFI itself, or it come from naturally IFI free? The cooling system, I'm suppose, yes, it with fans to create extra IFI or not?
No. So the question was about the cooling system, and I'm sorry, but I don't have any photos of the cooling system itself, but it is a noisy system, but it's contained within the shielded cabinet of the receiver system as a whole. It is an industrial cooling system, plug and play. It's used a lot in electronics, electrical cabinets, distribution boxes throughout Australia. And if I had a photo of it, and you're familiar with industrial cooling systems, you'd recognize it straight away. Would you say it's noisy? I wouldn't say it's noisy compared to, it's not as noisy as a normal air conditioner because it doesn't have the smarts of a normal air conditioner. Yeah, it's an industrial air conditioner that I think is relatively quiet. Yeah. But the cabinet itself, which a lot of design effort went into, is a very effective shielding system. It's a very good shielding cabinet. Again, it had to be custom made because there was no supplier in Australia that will produce one at the size and form factor that was needed. And it houses not only all the electronics, but the cooling system as well.
Okay, great. So let's move on. So let's thank Andy once again. And the commanders is going to do the second part of the story.
I'm just going to say one thing.
Yes.
It's very rare that you get the operations team sort of access to them that you do at the moment. So if you do have any questions, grab hold of them because, like I said earlier, they all wear other hats and they all have other jobs to get off to. And so feel free, just corner them over lunch or something and ask them all the questions that you want.
Okay. Thank you.
Cool. Thanks, Andy. Do you want that?
Cool.
Good morning, everyone. I'm Greg Sleep. I'm the MWA Data Manager and the Software and Systems Team Leader. I do apologise that I have a cold, so I may be randomly sneezing, coughing, or otherwise looking sickly. I do apologise. And I just want to say thanks to Andy for his talk. It was really good. And I must say that if your team is really cool, you don't really need to say you're cool. So speaking of the team, so I decided, given a 25-minute slot, instead of me doing all the talking, I would actually get my team up here to showcase all of the work that they're doing, and so that you guys can all get to know them and get to know what a talented bunch of people that I'm privileged to lead. So in this talk, you'll hear from everyone except for Jamie, who's over in Tasmania. He couldn't be with us today, but I'm doing his slides for him. Yeah, it's a very diverse group of people with different skill sets, and I think that reflects very heavily the fact that we have a very diverse portfolio of responsibilities in my team, because we're looking after software and systems all the way from the receivers producing their flood of data into the correlator, all the way down to the Curtin data center and then Pawsey for depositing data, and then getting that data out to users and everything in between. So it's a big job, and we're all got many hats, as Andy mentioned as well. So I'll just get started here. So I'll be talking to you about the data and archive side of things. I'll be then covering Jamie's side of things, which is the servers, infrastructure, and cybersecurity, and also the Calvin, MWAX Calvin and Beamformer. So that's the calibration pipeline and Beamformer work. And then I'll hand over to Andrew for M&C and new receiver stuff. Sorry, yes, I've got them in the wrong order there. Apologies. So I'll hand over to Christopher and then hand over to Andrew. Christopher will talk to you about the MWAX side of things, so the correlator and UDP capture and changes there. And then finally, Maureen will bring up the rear with MWA, ASVO, and data access. So in the data and archive side of things, we've been reasonably well prepared for phase 3's data rate challenge. So this plot here, a little bit confusing, but basically you've got along the x-axis, you've got the number of tiles. And then I've illustrated here with 3 different correlator modes, the amount of data that you produce with 1 hour of observing in those modes. So you can see that at 256T, the top right red dot there, you're generating 23 terabytes in an hour. If you're using the 10 kilohertz and 0.5 second correlator mode. If you use more generous frequency and time averaging, like down the bottom, the blue line, which is 40 kilohertz and 2 seconds, the amount of data generated after an hour is far more forgiving. But yeah, the MWAX correlator has been able to support all of these modes, and it's been really interesting and also nail-biting to start testing them out as the new tiles and receivers were coming online in fits and starts. And I'm happy to say that yeah, we're pretty solid in supporting all of the modes up to 256 tiles, and the system is holding up well. We had the 256T in mind from the very beginning of the development of the MWAX correlator, and ever since then, all of the systems we've been preparing for the day that we'd be turning on this fire hose of data. So some other stuff.
Hello, Bea.
Oh, hello. So other stuff going on in the data and archive world is we've had some of our data be migrated from one part of Pawsey's system to another, and luckily that all happened transparently. Pawsey did a really good job in making sure that that happened smoothly. And it was a good way for us to validate that the data that we had on the system is actually what we think we have. We're also looking at extending the archive out to external locations and trialing technology called Globus, and the diagram on the right-hand side there is an illustration of how Globus works. I don't have time to sort of go into all of that, but we've got various use cases where we're wanting to see if we can get data across the other side of the world, and that involves working with CSCS as well as the Bulgarian astronomical John knows what Bulgaria with Cayman. So working with him, and I blame the cold medication. I'm sorry. To test getting a whole bunch of the solar data moved over there and to see what we can do with it. Also, there's always investigations going on into how we can get the most out of our archive space, including compression. So Richard has a talk, I think, later today, so tune in for that one. That will be very interesting, and I'll be keen to see what happens there. This is just showing the archive growth over time. Currently, we've got about 8 petabytes free in the archive, which is great so that we can get all of this semester's observing done without worrying about running out of space. Thank you to everyone who helped in the most recent round of deletion nomination, because with your help, we managed to get rid of quite a lot of data that had very little value. And the process worked quite well because there were a couple of occasions where people identified data that they didn't want to be removed. And so we were able to then retain that for them so that they could then get another go at that. This is just the usual slide that's a bit busy that shows where all the data is in the archive. And the biggest slice there is other. But you can see that some of the big name projects are there, as you would expect. But we do have a lot of data across a lot of projects now, and it's no longer the case that any single project is really dominating anymore. So with servers and infrastructure and cybersecurity, so this is Jamie's side of things. I added this into Jamie's slides because I wanted to illustrate how much stuff behind the scenes is being managed to keep everything running from the software and systems side. And you can see in the bottom right corner there that we have 340 managed devices, and I think I'm not even counting everything, that have firmware, software, hardware, operating systems that all need updates, maintenance, patching, and so it's a really large job, and it's very good to have Jamie on board to spearhead looking after all that stuff. So in November 2024, Cairo was awarded $360,000 from the Curtin University Strategic Research Investment Funding Program for some MWA servers. So we were able to replace the aging MWA cache servers, which sit down in the Curtin data center and make sure that the data gets from the MRO over to Pawsey. And we're also able to create a new cluster called Calvin for calibration. So this will provide, or this does now provide, because it is live, near real-time calibration for MWA data as it comes off the telescope. So within about 6 minutes of a calibration observation coming off the telescope, we're creating the calibration solutions and storing that in a database so that it's ready to be used in future things like the real-time beamformer, which I'll be talking about in just a moment. We've done a whole bunch of IT uplift stuff over the last year especially. So this is basically to make sure that all of our systems are refreshed, that we're not relying too much on end-of-life equipment, which unfortunately when you've got a big project like this over a long period of time, eventually new becomes old and you've got to manage all of that obsolescence. So I won't run through all of those things there, but one of the main things that we did was replace our dependence on the CSIRO link and firewall at the MRO and replace it with a Curtin-based one, which we manage, which has improved our visibility and security a lot because we can now control that. There's a lot of next steps for this because it's an ongoing endeavor. but we're basically working on improving all of our processes, making sure we're secure, and making sure that we can safely serve out data and web services and other things to the world without exposing us as a security threat. Because out there at the moment, the internet is a wild place, and in our logs we can see that we're constantly under attack from various sources. So yeah, it's a constant effort to keep us safe. So Kelvin and the beamformer, I'll just quickly talk about that before passing on. So the Kelvin calibrator pipeline, as I said, it provides near real-time calibration. We use Beerly and Hyperdrive, so thanks a lot, Dev. And those servers are run under a Slurm cluster, just a very basic one, but it does the job. And they do the calibration process in much faster time than our previous hardware. So it's ready to go basically for the main use case of it, which is the next thing I'm going to talk about, which is the beamformer. So development is underway for the real-time coherent beamformer. So the idea is that this will reduce the need for large VCS observations, because we'll be able to do the beamforming in real time off the telescope, just like a normal observation. We're working through now all the details, but currently we've got Ian Morrison working for us, doing the signal processing, and we've got Bradley Myers as part of AusSRC working for us to, I guess, be the pulsar processing subject matter expert, so that we make sure that we make something that the pulsar and fast transients team can use and that they want. So yeah, so the data products will eventually end up in the archive and be served out from MWA ASVO, just like calibrator, sorry, just like visibilities and our other data. This will also set us up to participate in CSIRO's VLBI Project Lambda. So we're hoping basically to get a minimum viable product out the door early next year, so that's ready for some science testing in the next semester. And I'll now hand over to Christopher.
Hello, my name is Christopher Phillips, and since the start of last year, I've been responsible for maintaining the MX correlator software stack. We've been making various software improvements to the correlator in anticipation of the heavier load it'll need to deal with, while supporting either double the number of tiles, taking 256T actually quadruples the number of visibility products, or alternately increasing our sample rate by about 30% for oversampled observations. Now, we'd anticipated those needs from the start, as Greg already mentioned, so we knew we'd had enough compute capability, but it's always good to optimize the code a bit more, which gives us a bit more headroom for things going wrong, and also reduces our environmental footprint a little as well along the way, which is a nice little bonus. The first stage, now do I have a pointer? Yes, I do. I can only see it up there, not down here. No, never mind that. So the first stage in an observation that the MWX servers do is they actually capture a stream of packets of observations for just one 1.28 gigahertz channel for each of those, and puts together a fresh voltage file every 8 seconds. While that so there's the process responsible for the packet capture that's also busy reading the metadata for the current observation, calculating geometric delays, and doing the first phase of delay compensation. All these threads of computation need fairly careful coordination, and if there are delays from some inputs or some file outputs, things get slightly out of sync. So you need to be really careful that something that's waiting for something else doesn't end up with something else waiting for the something. And we were having a few issues until middle of last year, where every now and then one of the correlator boxes would lock up in this process. Something would go wrong because something was waiting for something else. And that would just freeze up, and we'd lose a channel's worth of observations for the rest of that evening and need a manual intervention to restart that channel. We've overhauled the state system that intermediates between those various execution threads and tracks packet arrivals, and eliminated a whole bunch of race conditions, and that particular subsystem is now rock solid. To the extent that one of my colleagues had actually forgotten how often they had to restart the system until I mentioned this going through the talk a few days ago. So I'm taking that as a good sign. That problem's gone. We also do a bit more logging of things like packet arrival times, so we can get a clearer picture of the causes of any packet loss issues. We'll have more about that from Andrew in his section of the talk. The next section after the voltage capture is the FX engine that does Fourier transform and then the cross correlations and then the averaging for the fine channels and the time averaging. We've made a number of optimizations to that stage. One of the larger ones was immediately after we do the cross correlations, the code that does that is designed for efficiency rather than for sanity of output ordering. And the immediate output from that is in a bit of a weird order that needs a bit of shuffling to get into a sensible order to write out. We used to do that reordering in a couple of passes to go to an intermediate format that we used to support, and then from that one to the one that we actually support now. We've rewritten that to just have a single pass that not only cuts down the number of passes, but we also write out the data in a more memory subsystem friendly manner. And that phase is now 3 times as fast as it was before. So that shaved a good fraction of a second off our 8 seconds and gives us a bit more headroom for things going on, which is always good. While we've been working on that, we've been making various changes, like we've been refactoring the code. I've shaved about 30% off the length of the source code, or about 700 lines, without actually adding functionality. The reason this is a good thing is it makes it easier for future maintainers to read the code when they're fixing bugs or adding new features, which includes me in a year's time. Means I'll be able to come back to it and make more sense of what I did a year earlier. We've also been adding some automated testing. So rather than at the moment, in the past, when we've added a new thing, we've had to check the new thing works and then try and think of things we might have broken, so go back and test those as well. We're adding a comprehensive test suite so that we can actually check that all the modes of observation still work with all the various flags. So we can actually just run a thing and let it run for a little while, and it can come back and say, no, Christopher, you've broken something. Rethink what you're doing before you release it into the world. So that'll be a bit simpler to stay on top of in the future. Right. I'm going to talk a bit about the fine channelization at this point. Just after we finished the cross-correlation stage, we've got about 6,500 fine channels, which we average down into a number of buckets, depending on the observation mode, usually between 10 and 80 megahertz wide, as I'm sure you're aware. Now, in critically sampled mode, the problem with having a sample rate that's only just enough to be able to represent the entire width of a broad channel, a cross channel, sorry, is you get a bit of crosstalk between cross channels. If you've got a filter that's flat enough to actually get your signal across almost the entire course channel, then that tail tapers off and you pick up stuff from just outside the course channel as well. Thanks to Nyquist, that then wraps around and then lands at the other end of the spectrum. And also because we have an even number of fine channels per course channel, when we center the center, oops, that should go back in. When we center the center channel, that leaves us with 2 half-size buckets at each end. And what we've been using that half-size bucket for is we grab all the energy from the top half bucket and the bottom half bucket and drop that into fine channel 0 for that course channel. Now that means that we don't lose any of the energy that lands into either end, but we don't really know which frequencies that represents, partly because of the crosstalk we talked about and partly because we're grouping stuff from 2 ends. That does then mean that, so the upside is we don't lose anything, we don't miss out on any little transient little spikes that happened in a little frequency that would have vanished if we'd thrown away that upper half box. But that does mean if you try and put together an observation by grabbing a number of course channels and then stacking the fine channels next to each other, every nth one isn't really part of the sequence because it's grabbing stuff from the bottom of a course channel and from the top as well. So that makes them, and Deb will talk more about that later on. What we can now do in oversampled mode is, because we're sampling at a high enough rate to actually distinguish frequencies that are just outside the course channel we're looking at, the filter goes closer to the edge and then drops off outside of that. And we now have the option, and what we've been doing as of about a week ago now, is for fine channel 0, we pick up some energy from just below the left edge of the band. You can see in the lighter blue area there, that's actually, the left side of that 0 box is actually comes from the next course channel down, but we have access to that because of the oversampling. It looks like we're missing stuff at the right side, but we pick that up from the next course channel out because that's doing that half channel overlap as well. So if we can concatenate all those boxes together, we then just get a nice evenly spaced sequence of fine channels across the entire observation. More of that from Dev later on. I'll pass you on to our next speaker.
I'm doing the M&C stuff. I have been doing M&C software for the MWA since about 2007. The latest stuff, we now run the correlator in critical sample mode in 256 tiles at all times. It used to be that we changed the configuration to support whatever number of receivers we wanted to use at that time. That was a very slow manual process. Now we can schedule an observation with whatever set of tiles you want for that observation, and only the tiles you've specified as being interesting for that observation are saved to PAWSI. The rest of it is dynamically just dumped at the output stage of the correlator. So you can use any number of tiles you want for an observation. And in fact, that's true for smaller number of tiles. In the future, if you'd like to do observations with 16 tiles and save space in PAWSI, we can support that. In the future, I'd like to be able to support reduced number of channels as well. A lot of people aren't interested in all 24 channels. So we could even do things like an observation that has 256 tiles for one course channel and 64 tiles or 128 tiles for the other 23 course channels. Anything to save data at PAWSI. We're data limited, not time limited on the sky. In oversampling mode, we run with just 128 tiles, a shower receivers that can do oversampling on the inner core and the hex tiles. Changing between critical and oversampling requires a complete correlator shutdown and restart and reconfiguration. That takes about a quarter of an hour. Was manual as of like a week before the start of the semester. We could do it automatically. We schedule a special correlator mode change observation. A daemon sits there, recognizes that, shuts down the correlator, changes the config file, starts it up again. But that gives you about 15 minutes of dead time in between your critical sample mode and your oversample mode. Most users don't want oversampling. They want longer baselines. The telescope will stay in non-oversampling mode by default. Oversampling mode observations are scheduled in blocks for EOR. So we'll get, a mode change, 6 hours of EOR, a mode change back again. And that will mean we can't do triggered observations when we're in oversampling mode, unless the people doing the triggering want oversampling. So there's a new web service to allow you to detect the current mode and choose whether or not to send a trigger. Managing all of the new shower stuff was a lot of work. We've got 8 field cabinets. We need to do setup of the receivers. We need to change the state for observations. We need to monitor the White Rabbit clock system. We need to power cycle it up to 3 times to get it to actually start producing a clock when you turn it on for the first time. So everything in these field cabinets and in the main building is connected to a network PDU, so we can turn them off and on again until they work. Classic IT solution. We need to monitor the health of the field cabinet, temperatures, voltages, whether the clock is working, using a pair of small Linux servers, actually Raspberry Pis, in each of the field cabinets. And there's another 56 of those in the long baseline tiles. We need to send pointing commands to the tiles using Carrier's new beamformer controllers, speaking a messaging protocol called MQTT. And we needed all of the metadata, correlator control, and web services and stuff to support all of the new tiles and to support oversampling mode. Just as an example, one of the issues we've had is packet loss. Network switches are rated for a given throughput in terms of megabits per second, but throughput on a normal network is random. When you have 16 shower receivers containing a total of 32 FPGAs, all synchronized via atomic clock, the packets come out at precisely the same instant. So Jake and I have spent a lot of time looking at this output, which is a 3D visualization tool called Napari, and we can pan and zoom around and see artifacts. Like you can see a couple of receivers here that have lower than average packet losses. And that's because this is the 34th receiver, and there are no packets coming after it. It's a bit of a gap before receiver 1 starts sending data. But while it looks grey, typical packet losses are about 0.1%. So yeah, a lot of time has been spent doing stuff like that. And now I'll put you on to Moran to talk about getting data out.
Thank you. So I'll give a quick update on ASP1 data access. So do I get a 0-minute warning? Okay. Sure. All right. Thank you. So for those who do not know what ASPO is, it's Australian All Sky Virtual Observatory, or simply All Sky Virtual Observatory. So that gives the Australian data to the researchers. So MWA is one of the 5 nodes in ASBO. So MWA ASBO is the data portal to access MWA archive. We have the dashboards for browsing through the observations, and we provide it through the Vivo tab service. And we also provide command line tools for the users to access the MWA data and download their data. And these are some of the stats from last year. So we have served out 10.8 petabytes of data, and through a total of 113,000 jobs. So we also handled more than 2 million logins. Most of them are API logins, because most of our users use our command line tools to log in through the API, use our API servers to submit the jobs and download the jobs. And that picture depicts, the organizations that use our data. So totally 36 organizations and several independent users we serve. So you can see 72% of the data is being downloaded by the people from Curtin University and the MWA project members. And moving on to the key announcements we have done in the last year. So during November 2024, we migrated our job processing from Caravalla to Cetonics. So if you do not know what Caravalla and Cetonics are, they are the supercomputers hosted POSI. So we heavily rely on POSI's supercomputing system to do our job processing. And with the new Cetonics, we got more CPU nodes and more CPUs per node and more dedicated nodes to MWA. So we got 10 worker nodes and 2 data mover nodes. So with all our tests, we could say it is 30% faster than Caravalla, but it comes with challenges as well. So with the new Cetonics nodes, we are missing the NVMe, which is like a solid state drive attached to the node. So we are missing that. So when the data is huge, it is the pre-processing of data is taking much longer than we expect. So POSI nodes, other nodes have NVMe attached to that. So we are constantly working on with POSI to utilize those nodes for our job processing for at least the huge jobs to push them through as quick as possible. And on Feb 2025, we implemented the new calibration service. We usually, when a user asks for calibration, so we say, sorry, user, come back after 2 days to get your calibration solution. But with the latest change, we have used webhooks to, when a user asks for a calibration, so the jobs contacts the calibration service Greg talked about before. So we put the job in the queue, and once the calibration solution available, we process the job. So user doesn't have to come back and resubmit the job, re-download the things. And on March 2025, we done update on ASO job states. So usually we provided only 3 states like queued, processing, or completed. Now we have expanded it to every part of the process. So users are well informed about what the job status is. So and they can manage their job better. And we also released the major client versions to v2.0. And in May 2025, we done a DUG delivery. So DUG is a commercial supercomputing center in Perth. So some of our researchers wanted to use that supercomputing. So we implemented a DUG delivery. So we worked with DUG to find a solution to how securely we can transfer the data from POSI to the DUG supercomputing center. It also comes with a challenge that we have to now use a third-party tool provided by DUG to do the transfer. So we are in constant communication with them to keep improving. So they have given a lot of fixes and the latest releases of that tool, and currently it is working fine. So if you find any problems, we'll be in touch with them to get it working. And in future plans, we have planned the imaging pipeline. So this is a very quick and dirty look of the image of the observations. So it's just designed to help the non-MWA experts who doesn't want to know download the data and to know what kind of image they are going to get. So we just planning to create a basic imaging to just let them know that this is what is in the data inside. So with the, it is going to be with very limited parameters. The very simple step to be probably thinking of using WSClean for the basic imaging. And we are also planning for open API. So our servers will be improved with the better API handling, and the Swagger documentation comes along with that. So users can use the Swaggers to better know about our API and better integrate their flows like the workflows to submit the jobs and manage their jobs. Also, we are planning on doing a AstroQuery integration. This is something like once it is there, you can simply do a from AstroQuery import MWA and MWA find jobs or submit jobs. So that will become that easy to submit your jobs and manage your jobs. So it will make it very seamless integration with the user scripts. And yep, that's it.
Brilliant. So thank you, Greg and team, for all the hard work you guys have been doing. So the data appears like, magic when you press the button. Anyway, so we are a bit out of time, but we can take maybe like at the most couple of quick questions from the room while we are switching the speaker. Yeah.
Thanks, folks. It's really amazing. Thanks a lot for all the hard work which you guys put in. A couple of questions, perhaps the first one for Greg. How many beams are we thinking of at most? Okay.
Thanks. Yeah, so we don't actually know yet. So we're going to be running on the MWAX hardware, so the same that does the correlator at the moment. So we've got decent GPUs, decent RAM, and we think we can do maybe a dozen at once with different pointings. But we're just not sure until we actually get the prototype code to a point where we can do some benchmarks. But that's the hope, is that we can do that.
Thanks. That would be fantastic. And perhaps quickly for Andrew, do we expect to have subarrays anytime soon, or maybe not so soon? Yeah.
We can use subarrays now, and people have been using subarrays and observations.
Okay, wonderful. Yeah.
So that's certainly something we can do.
Perfect. Yeah. Thanks.
Any quick burning question? If not, let's thank the entire team. But as Andy said, it's a pretty rare that you get to see all our ops team in a single spot, and so it's your opportunity to catch them and raise your questions and concerns about in the next few days. I hope all of you will be here. Thank you very much. So next we will have Dev Nal talk about an issue that has been giving us sleepless nights for quite many of us for quite a while. So over to you. I will give you 5 minutes.
Yeah. Thanks. You'll have to yell out because I get tunnel vision. Thanks. So hey folks, my name's Dev Noel. I use they them pronouns. I'm from the Australian SKA Regional Centre. So in the previous talk, you would have heard about some recent upgrades. And I'm going to talk about the impact these will have on one of the MWA's key science activities, the epoch of reionization. And I'll provide some updates on recent progress that has been made in our pre-processing, calibration, and our ionospheric subtraction software. Great, that works. So one of the goals of the epoch of reionization experiment with the MWA is to study the early universe with the redshifted 21 centimeter neutral hydrogen signal. It's a really faint signal compared to the foreground signal from the rest of the universe's history. So the aim of the game is to refine our techniques to separate the signal from everything else. It's pretty crucial to have an in-depth understanding of not just the foregrounds, but the systematics in our instrument. So we've been making great progress, and I'll defer to the talks tomorrow for more details here. But until recently, we've been at the mercy of a subtle but very troublesome systematic in the MWA signal chain. In order to explain that, I'll need to explain how power spectra work, and I know that we have a lot of diversity in the audience. Not everyone's here from the science background. They've got a lot of engineers, so I kind of thought I'd explain power spectra a little bit. The basic idea is we're trying to attempt to measure how the distribution of neutral hydrogen changes over redshift. And since we're talking about the variance of a brightness temperature signal over cosmological distances, we have to use these co-moving coordinates for everything to make sense. And this results in some of the most cursed units I've ever seen, millikelvin squared per cubic Hubble megaparsec. So if our brightness temperature distribution, which is the T of co-moving R, then the Fourier transform that is, we'll call it squiggle T of co-moving K. So we're trying to measure squiggle T K. We can split out the co-moving wave number K into the components that are perpendicular and parallel to the line of sight. So firstly, we have the transverse component K perp, which is perpendicular to the line of sight. And yeah, in an interferometer array, if you have a baseline at a given length B, that happens to just sample the Fourier transform of the brightness temperature at the wave number U, which is given by the length of the baseline divided by the wavelength. So short baselines probe large scale structure, and long baselines probe small scale structure. That's the important takeaway here. I have to remind myself about this constantly. It doesn't make sense to me, but yeah, when it works, this is the way it works out. It's not very intuitive. But yeah, there's a linear relationship between K perp and U, and it's based on a scaling factor based on the co-moving distance at the redshift that you're looking at. And then we have the line of sight K. So we'll flip everything over 90 degrees and talk about the line of sight. If we're only looking at the redshifted 21 signal, then as we sweep along frequency, we're also scanning along co-moving distance. So this means that we can also probe different spatial scales with a Fourier transform along frequency. This brings us to delay space, since the Fourier, which is the Fourier dual of frequency, is time. So this time, our wave number is a variable called eta, that little n symbol, and big delays oscillate rapidly in frequency, probing small scale structure. So big eta is small scale, and small delays oscillate slowly in frequency, probing large scale structure. And then, so finally, we can put that all together. We've covered both axes of the two-dimensional cylindrical power spectra. So you start by gridding the visibilities, then you take a Fourier transform along frequency and average all the visibility, all those components in concentric rings around K equals UV equals 0. And so the clever part of this is that the majority of the bright foreground signals are nice and smooth, spectrally smooth, and that means that they're limited to within this wedge, which is denoted by the horizon limit and the beam limit. That is a delay that depends on your baseline length. Those are the maximum possible delays of a perfectly smooth signal. So that means that, yeah, mostly your foreground is going to stay in the wedge, and the EOR signal, which we predict should be spectrally varying, that's going to end up in the window. The problem is, for the last decade of MWA, that's right where the coarse channel harmonics are. And this one of these this power spectra is one of the best ones that we've done with phase 1 and phase 2. And no matter what we do, we can't get rid of that little those little coarse channel harmonics. But yeah, those 1.28 megahertz coarse channel harmonics. So why are they there? We just got to go do a brief overview of the signal chain. We've covered a lot of stuff already in previous talks, so I'll kind of skip through it. But I'm mostly talking about the receiver and the correlator. It's not really relevant. The tiles doesn't really make much of a difference. But the receiver does signal conditioning and is where you do the digitization and coarse channelization. And it sends 24 of those coarse channels to the correlator, and the correlator splits the coarse channels further into the fine channels and computes the visibilities, which are the product of every pair of input signals. Just really quickly, there's the old receivers. They're amazing that they've lasted this long, but there's quite a few issues that are improved in the new receivers, and one of those we've already mentioned the fact that these old ones are critically sampled, but not a lot of attention is paid to the bit occupancy, which has also improved quite a lot. So the new receivers have much better bit depth, which gives you a much higher fidelity signal with better signal to noise, and of course having modern hardware is also a great improvement for reliability and all those things. And just quickly on the correlator, again, there are some improvements here in the bit depth as well. So there is also better possible resolutions. You can go down to higher resolutions than before. And there's some new features that have come recently, like the delay corrections, which are called fringe stopping in the correlator. They're also called geometric corrections in BLE, just to be confusing. And then there's the other thing, the PFB bandpass correction, or the D-ripple, which is something that's quite necessary for dealing with the oversampled data. And just quickly, bit of background and bit occupancy, why that matters. If you have fewer bits, then you have more quantization errors. And so when you're trying to digitize or represent a smaller value in your digital system, you're going to have larger fractional error. And then the larger values, if you don't have enough bits, you'll also have risk of clipping or wrapping around, which we've seen before when the gains aren't set correctly. And yeah, so what we use to mitigate this is the digital gains, because the values that we're digitizing can span a really huge number of orders of magnitude. It depends completely on what frequency you're looking at. The cable pass bands can be completely different, especially at really low frequencies. And so all the digital gains have to handle all these different possible digital values that you'd have for every channel. And so that's why there's digital gains set separately per receiver and per signal chain. But yeah, there's even more tuning that could potentially be done. So this is a comparison of what the previous orange critically sampled bandpass used to look like, and what the brand new shiny oversampled passband looks like. So the critical takeaway here is that the critically sampled passband has this 60 dB signal loss. It's at the edges, which means that if you're already kind of close to the minimum value that you can accurately represent in your digital system, it gets even worse. You lose 1 bit effectively at the edges. That leads to quantization effects even on the new receivers, even on the receivers with the right bit depth, with better bit depth. It still is an issue. So the oversampled PFB does more samples than it needs, and it throws away the edges, and you get these much better edges, 0.5 dB signal loss, and the ripple. you can correct for that in the correlator at the highest, at the ultra fine frequency, rather than doing that in your pre-processing step, post-correlation pre-processing step, where you lose, where you've got fewer channels. So that's what derippling. That's why derippling is great, because it gets rid of that ripple. So this is one observe. So I've been able to work with the operations team to get some sample data from the new system, and this is one. So this is I'm going to progressively get better and better power spectra as we get out of this. So this was observed a month ago, and there was this issue that we had where the fine channel 0 that Christopher described was behaving exactly like the coarse channel, the critically sampled correlator used to. So it took the power in from the edges of the left and right channel, and it didn't look good. So we would typically, so in order to try and mitigate that, I flagged it out, and that 40 kilohertz channel was not included in the analysis. So even if there was power there, it was flagged out, but it still causes these coarse channel harmonics. Even if you have just one 40 kilohertz channel flagged, it still causes this harmonic, and it's an issue. Back in phase 2 and phase 1, we had even more channels that were needed to be flagged out, and it was even more of a problem. But yeah, with 1 hour of data, you can very clearly see the coarse channel harmonic. And when Christopher made this fix recently, that went away. Woo! Just to say that we're still not done yet, but those coarse channel harmonics went away, and there's 2 new mystery signals there as well, and we'll go in, we'll have a look at those, because we've never been able to see these before. These were buried under the coarse channel harmonics, and there's some new stuff that. Yeah, this was only observed a couple of days ago. That's why some of the slides are a bit rushed. But we can do better than this. So we'll talk about some of the pre-processing stuff that we do, pre-processing and calibration and stuff. MWA is on a fantastic radio quiet zone, but of course, we get all kinds of interference still from aircraft and satellite constellations. It's getting worse, but there are ways that we can deal with that. We also, depending on the weather conditions, we get digital TV from 800 kilometers away. That is a really specific signal that kind of doesn't always get flagged out by certain flagging algorithms. So yeah, there's all kinds of potential sources of interference. So Beely is the pre-processing software. So we integrate all the pre-processing steps into this. It has been integrated into the ASVO, so most people don't really need to think about pre-processing anymore, because you just download it. It all happens for you automatically. But yeah, it takes in raw data and does flagging and corrections, and it uses a couple of different flagging algorithms. It also does Van Vleck correction now, which is no longer necessary. But back if you want to look at old data, this is quite. It can make a big difference for correcting these digital, digitization, quantization artifacts. But yeah, don't need it anymore. There's also a couple of different flagging algorithms. So we've got AO Flagger. These bottom 2 are showing the difference that it makes for. So AO Flagger is just looking for signals that anomalies in your each baseline one at a time, and it flags those out. So wherever there's more green, that means it's found things that stand out from the rest of the visibility that it's looking at. So at the bottom, we've got phase 1 with and without Van Vleck correction. Phase 2, we don't need the Van Vleck corrections for that anymore. And there's something, you'll notice that the certain channels have this 1.28 megahertz coarse channel quantization artifacts. But then we look at phase 3 and it's so clean. But if you look really closely, there's something I haven't figured this out yet. This is really hot off the presses, but there is some structure happening at twice the frequency, half the frequency of the course channel. There's two, I don't know, the structure is repeating on the order of like half a course channel for certain frequencies, not for other frequencies. And I think that's related to digital gains. It's potentially that some like 1 or 2 tiles might just be just below the kind of threshold of good values. So more research needed. Anyway, so that's AOFlag. We also have this other popular algorithm called SINS, the sky subtracted incoherent noise spectra, finds stuff that AOFlag doesn't, but it can tend to overflag, and so there's a bit of tuning that's needed for it to be like generally useful. But we do find get a lot of value out of it just for visually inspecting RFI. This is just some of the RFI that it finds. It's mostly really good at picking up TV. As you get further and further on, you find there's TV, but then there's a whole bunch of other things. That's just a dead course channel. Don't worry about that one. But there becomes you start to see like different morphologies of RFI as time goes on, and yeah, it gets more populated, I guess, more crowded as well. But yeah, it's really inefficient. You can't run it on Sotonix because there's not enough memory. It's so slow. So that's why we're integrating it into Beely, which is way faster, way better memory performance. What you can also do is you could take your flags and export them to FITs. There's this mode I'm working on. It's a work in progress, but you can just open your flag files with Carta and see like a spectrogram, a waterfall plot of your flags for all the different algorithms. It's going to be a while away before we have like a flag mask that you can actually like apply to your flags, but it's really useful if you just want to inspect the data quality without downloading the whole observation, and it's been quite useful for that. What have I got? Yeah. One of the things that I'm talking about for making the power spectrum better is hyperdrive. It does ionospheric subtraction. I have some cool slides on it, but I think I'm just going to skip over them, and you can refer to that later. There is one cool thing that's been added recently, which is the proper ionospheric subtraction, and there's a lot of tricks that you got to do to make sure that the subtraction doesn't blow up. But we've kind of figured it out recently, and it's performing a lot better than before, and that's all released, and it will soon be citable even once ERSI AP-RASC proceedings are published. You will actually be able to cite hyperdrive in your paper, which is great. So now, let's look at this is the one from before with no subtraction. So no hyperdrive ionospheric subtraction, but hyperdrive calibration and pretty much all the standard other stuff. And this is what happens when you do a subtraction. Much better performance, right? You can see that the long baselines that pick up the small scale structure have a lot less power in them because the point source model that we give to hyperdrive has been subtracted quite well. Thanks. And so yeah, but you can also see that you can see these peaks, these mystery peaks, even clearer now. Now that the rest of the stuff is gone. And yeah, there's a peak at 0.6 and 0.9 K. So just digging a little bit deeper, let's compare what we had. So I had that observation from a month ago that had the gap in it, where we flagged the fine channel in each coarse channel, and then I had the one that was just observed with the fine channel fix. Both of them a month apart have the same 0.6, the same interesting structure at K equals 0.6. Can't really tell you whether they both see the K equals 0.9 because that just happens to fall in the second harmonic of the coarse channel. Yeah, they're a month apart. They're seeing some interesting peak, but only in YY, not in XX. That's interesting, isn't it? yeah, so maybe you're starting to think, well, if it's seen in YY and not XX, then maybe it's the galactic plane or something on the east or west horizon, something like that. So I thought I'd dig a little bit deeper, do some slicing in K-perp. So just taking a few different slices from red to blue. I know this is probably very difficult to really see much. We probably need to do a bit more analysis on this, but what happens is that peak that we're seeing in K equals 0.6, it starts to slowly die off around K equals 0.03. And that might be, I don't know, this is purely speculative, but it might be suggestive of a feature that's around about 2 degrees in size, just based on the which K values that see it. But it's the galactic plane. If it was flat in spectra, you should see it on the horizon line. We're way outside the horizon line, so it's probably. Well, I'm not going to speculate. Maybe others can suggest ideas in this. And yeah, the other thing before I go, the second, the other thing at K equals 0.9 does happen to fall in the second harmonic. Maybe if anyone has any suggestions on what that might be as well, I'd love to hear them. So I'll acknowledge, thanks so much to the operations team for going above and beyond to make sure that we had really good quality data this season. I know EOR is very picky, and we asked for a lot of different revisions to correlated code and lots of questions from Jake about about digital gains and all that stuff. So really appreciate it. I did all the processing on Doug for this, so it wouldn't have. It was such a the time between observing and the talk was probably ill-advised to do a talk. Submit a talk before the observations for that talk are even been conceived about. But if because I was able to have access to Doug, I got those observations processed very quickly. It took less time to process them and do all the ionospheric subtraction on the GPUs and stuff. Took about 8 hours, and that was me being polite, but and not using all of Doug at the same time. But it took longer than that to download the observations or to get through the ASVO queue, because there was a lot of people downloading stuff in the last 2 weeks. So it took about 24 hours to get the stuff downloaded, and then about 8 hours to process it on Doug. Would have taken a lot longer if I'd used a different supercomputer. So I'm very, very grateful that we had access to Doug, because this talk probably wouldn't have been. You would have probably only been able to see the observation with the gap, and you wouldn't see the new one if it didn't have access to Doug. So very much appreciate that. Thanks.
Amazing amount of good work there to understand the new system, and it's a pleasure to watch your presentation and see all those great slides. So time for questions for Dev. Let's take questions from the room.
Hi, Dev. First of all, congratulations to you and everyone else in this. This was an awesome talk. I was on tenterhooks the whole time. You're a legend, so forth. Really cool results. So you've done a lot of work on the software side of things. I think a lot of the software you've developed, I want to use it for instruments that aren't MWA. Have you thought about how that would translate? I think there's a lot of potential impact here that goes well beyond just these plots, which are cool, but I have trouble seeing them.
Yep. It would be great. The thing about I guess if in order for me to be able to work on something, I have to have the support of OzSRC. It has to be something that meets our it's I would love to get hyperdrive to work on every telescope and be even faster and stuff like that, but we would need support to be able to do that, right? We need there's a lot of work there. So yeah, it would be great to be able to do all that, but if like maybe you can find more developers to help out, I'd love to walk people through that, and I'd love to get more developers working on it. But yeah, there's not much I could do.
I realize you are one person, and rest
Yeah.
assured I've been singing your praises to everyone I can internally with CSIRO. But yeah, that's awesome, especially the SINS method in BLE. I want to try to abuse that as well. So
Yeah.
yeah, no, thank you very much, and huge congratulations again.
Great. Got more questions? Oh, yeah.
Thanks, Dev. They're awesome results. One of the great motivating figures behind the MWA and EOR science case was Frank Briggs, who hasn't been connected to the project for a little while now, but Frank described the EOR experiment as peeling back the layers of the onion, and you've perfectly demonstrated that in your talk. When you resolve an issue, you just find the next one, and I think you can expect when you've solved this one to find the next one and the next one.
Mm-hmm.
That's the way it works. I couldn't quite figure out what the percentage improvement, if you like, is between, like, you had artifacts with some height for the coarse channel artifacts, and then you got rid of that and saw this next one further down. Is that like 50% down, 10%, 0.1%? What's the, how many layers have you taken off here?
I might have to put that on notice, and maybe Catherine Redeemer and I can figure out like a good way of quantifying that, because that's something that I've not quite done. These were made like very, very recently. It's all quite hot off the press. It looks pretty good on a graph. This is in log, so any of those peaks are what, like 2 orders of magnitude higher than previously. Yeah, than without the peaks. So visually it looks great, but coming up with an actual number probably needs some help for that. But maybe we can come back to you with an answer later.
Thanks.
Hi, Ron Eakers here. Thanks, Dev, and great progress. But I realize my comment here is not going to help given the path you've taken, but might be something for people to think about. Quite a lot of these artifacts, the initial harmonics, come from the fact we've digitized the signal. Now, it kind of hurts me. We have beautiful analog waveforms come into a telescope, and we turn them into a bunch of numbers, which is a very ugly process. If instead you start replacing some of these digital procedures by analog, you may avoid some of these problems.
Maybe. I loved your talk at ERSI where you showed the quantum was it correlator or beamformer? Yeah, yeah. That was a pretty impressive thing. But I guess we got to do what we can with what we got. I don't really have that much control over being able to overhaul the digital system and replace it with an analog one. But it'd be pretty cool, maybe. Yeah, it'd be probably a very big design process to figure out if that's all feasible.
Great. So I